Okay, this last video segment is to take us through prediction, and we'll talk about simple prediction, we'll talk about multiple prediction, and we'll talk a lot about what's called the standard error of the estimate. I think the material in this part of the packet is critically important. It really fills in a lot of the gaps where we couldn't go with the PowerPoint slides and with the material in the textbook. So I think this will put it together for you nicely. Bear with me for this very last of the video series. Here we're going to be talking a lot about what we call regression or prediction. Many of you already know, you've done the book reading, you know there's something called simple prediction. And in the case of simple prediction, what we're doing is we are predicting something we don't know, that is an unknown y-score based on a given x-score. So we might, for example, predict the number of pull-ups you can do based on your body weight. We might, for example, predict what your VO2 max is based on your 1.5 mile run time. We might, for example, predict your percent body fat based on the sum of your skin fold measures. Again, we're making a prediction. It's not for sure, so it's going to involve error. The general idea of this simple prediction is that we have a y variable, or what is sometimes called a criterion or dependent variable. We're predicting that based on the value on our x or our independent variable value. We put this into an equation. That equation has a b value and a c value. The b value we're going to learn is the slope. The c value is the y-intercept. And the general form of this simple prediction, where we have one predictor, is that the predicted score is equal to b times x plus c. So the way we develop these prediction equations is we start with people who have data on both our x variable and our y variable. So we take 50, 100 people, hopefully even more than that. And what we do is we develop this simple prediction equation by collecting their data. We have a score for everyone on their independent or predictor variable, such as their body weight. And we have a score for everyone on their y variable, such as the number of pull-ups that they can do. We then calculate a b and we calculate a c so that we could plug it into this prediction equation. All right? So how do you calculate that b? Well, these are the terms, all right? To calculate this b value or this slope value, we need to plug in the number of pairs. We need to plug in the sum of the x times y's. We need to subtract from that the sum of the x times the sum of the y's, and then divide it by these terms that are shown here. Rather than do all of this math, most of you have a two-variable calculator, which I've asked for you to purchase for this class, which will automatically spit out for you, given a number of x values and a number of y values, what the slope or the b value is to put into this equation. Similarly, you can calculate the long way the c value, or what's called the y-intercept in these equations. And what we do for that is we take the b that we've calculated in the step above, we plug it in here, we take the mean for our y's, and we subtract our b value times the mean for our x's, and that gives us our y-intercept, or the c's. Now I would once go through the long way, see if you're able to calculate this formula for the prediction line or the line of best fit in this manner. But certainly all of this you'll be able to very quickly, efficiently check on your calculator. So the way that this works is we develop this formula, we develop this prediction equation, and then in the future, all we need is that x variable in order to then predict what the measure will be on y. So we're using our line of best fit equation that we've developed to plug in now a value for our x, our predictor variable, in this case maybe body weight, and now we can estimate or predict what your value will be on y. Now the problem is, when you make a prediction, there's going to be error. So we have to always recognize that, and we know that we can index the degree of error, we can index the degree of accuracy of our predictions in really three different ways. The first and the second way we've already kind of talked about, and that is we can look at how strong the correlation is. The higher the R value, the closer the points are to the line, the less error. Similarly, the higher the R squared, the higher the coefficient of determination, the closer the points are to the prediction line, and the less error. The last thing we're going to be introducing is what's called the standard error of prediction. It has a million names. It's the standard error of prediction, it's the standard error of the estimate, and this standard error is error. So we are going to look for a low value for this in order to have a fairly accurate prediction. So let's move on, and let's once again note that the general form of our prediction equation looks something like this. Our y predicted, or what's sometimes indicated with a y with a little carrot top on top, we call it y predicted or y hat, is equal to this slope times your x value plus c. The slope, again, is the change in y over the change in x, the change in our prediction for a given change in x, and the slope of the regression line is going to have the same slope or direction as does the correlation coefficient between these two variables. The c value is what we call the y-intercept value. It's the value of our y when our x is equal to 0. What I think I'd like to do now is begin to focus on the thing that's probably the most difficult concept in the chapter, which is the error in prediction. Once we have developed our prediction equation, once we've developed our line of best fit or regression equation, we recognize that that prediction will not necessarily equal the true y value for that person. The only time that that is going to happen is when we are on that line of best fit and our correlation is actually a -1 or a 1. So there's always going to be error involved, and the error for a given individual is given by this equation. So we have here that error is really going to be the distance from the y value of that person. That's an actual score, and we're going to take from that now the difference. All right, the error is the difference between the actual y and the predicted y. It's sometimes called the residual score, and this would be the case for a given subject. We've walked through this example in the slides, and we saw that for subject number 3, we're going to predict based on their weight of 140 and this line of regression, this line of best fit, that they do about 8 pull-ups, when in fact they do 12. The error is the difference between their actual score and the error, so that makes for 4.03 push-ups. Here is the regression line or the prediction equation. We can see it takes the form of y hat or y predicted is equal to b times your x value plus your y-intercept. And when we plug in these numbers for the guy that's 140, we predict that he's going to do just about 8 pull-ups. Interestingly, the sum of all of these individual errors is going to be 0. And the reason is actual scores are on either side of this prediction line. They kind of balance out in that the error here, the error here, the error here, the error here, where all of these actual scores are below the predicted, are kind of balanced out by the error here, the error here, the error here for scores that are above the prediction line. So the sum of these individual error scores is always equal to 0. Makes sense. I hope this is kind of going ding, ding, ding in your head, because if you remember, we talked about deviations around the mean when we had a normal distribution, and those deviations are always going to sum to 0. Only here we have the sum of these error scores. The difference between the actual scores and the predicted scores is always going to be equal to 0. So we have to find a good way to kind of index the degree of error. How big are these differences between the prediction and the actual scores on average? And for that, we're going to use the standard error of prediction, or what is called the standard error of the estimate. Most often I'll abbreviate that with the SEE, okay? The SEE. This SEE is going to represent the average deviation of these error scores, okay? And remember, we couldn't have gotten an average by summing up all these errors and then dividing by the number of scores, because the sum of these errors is always going to be equal to 0. So now let's look at the standard error of the estimate. The standard error of the estimate is always a plus or minus value, as it's the error of the actual scores around the prediction. Some scores are above, some scores are below the prediction line. So whenever you see an SEE reported, remember that it actually is an SEE that is the plus and minus error around the prediction line. So let's take a look here at what the SEE again represents. It represents the average distance that the observed or actual values are from the prediction or regression line. Okay? And we could calculate this and we could come up with an exact number, but that looks like a lot of math. And we can do that very easily in Excel if you're interested in doing that. There's actually a symbol for this if you've been through the entire Excel packet. More often than not, we're just going to estimate the standard error of the estimate. And the estimated standard error of the estimate has, of course, different symbols. It can be SEE, it can be SY dot X sub Y dot X, or it can be S with a little e down here as a subscript. In each case, we simply calculate this value to indicate how much error there is by taking the standard deviation of the y scores and multiplying that by the square root of 1 minus the r squared, or 1 minus the coefficient of determination. So this is not a hard calculation. This should be done in an easy step. And what I want you to know is we are calculating the estimated standard error of the estimate. It is error, and the theme here is we always want a smaller standard error and a larger coefficient of determination in order to know that we have a very accurate prediction. Okay? So, what you're going to see here is this error around the prediction looks something like this. Okay? Here is the predicted score. Here is the standard error, and the y predicted is going to be plus or minus 1 standard error of the estimate. That captures for you what the error is. Let me re-say that, that the prediction, all right, we're going to make a prediction. We're going to predict your VO2 max. We're going to predict your likelihood of falls. We're going to predict your body fat. But there's error in that prediction. That error is indicated by the standard error of the estimate. If we take that prediction and we go plus or minus 1 standard error of the estimate away from that prediction, we will capture 68% of the actual scores. If we take that prediction and we go plus or minus 2 standard errors of the estimate away from it, we will capture the middle 95% of the actual scores. So you can see, I hope, that this kind of parallels our understanding and interpretation of the standard deviation. The standard errors, the bigger the standard error is, the more variance around the prediction, the less sure you are of the prediction. I certainly, if someone were estimating my body fat and they told me the standard error of the estimate is 2%, I would be pretty happy. Whereas if they told me the standard error of the estimate was 10% body fat, that would be a very inaccurate prediction, because many of the actual scores are far away from the prediction line. The way we can depict this is graphically. We have a prediction line, and then here are actual scores. Here we have another prediction line, and here are accurate scores. The actual accurate scores. You can see that if I had to ask you which is the more accurate prediction, if this was the scenario, the actual scores are very close to the prediction line. It's going to be much more accurate than this scenario where the scores are much more spread out. The standard error of the estimate is going to be greater in scenario B. This is not as accurate as of a prediction. So I tried to, in the previous slide, show you what is really meant by all this standard error of the estimate. You can see here that we have a y-hat or a prediction line. And then we have actual scores, which are indicated by the dots here. It turns out that most of the dots are near to the prediction line. It's kind of like little normal curves indicating where in the distribution are the scores. In this case, where in the distribution are the errors around a certain prediction line. So what you can do is you can figure out what the standard error of the estimate is. You can go, what's the prediction plus 1 standard error? What's the prediction minus 1 standard error? And 68% of the actual scores will be in that band of plus or minus 1 standard error from the prediction. Okay? So, not all y values will fall on the line. There is error in prediction. That error in prediction is indicated by this standard error of the estimate. You take your predicted score, you go minus 1 standard error and plus 1 standard error around that prediction, and you've now captured about 68% or 2/3 of the actual scores. If you were to go and take the prediction line and subtract from it 2 times the standard error and add to it 2 times the standard error, okay, you would capture about 95% of the actual scores or actual dots. So there's a real parallel here in our interpretation of the standard error of the estimate and our interpretation of the standard deviation. So you can refer to the interpretation handout, but why don't I kind of walk you through this interpretation, and let's for a minute assume that we are interpreting, in this case, VO2 max. So what we might say to a person, and I'll use Joe again. Hi Joe, our best estimate of your VO2 max is 50 milliliters per kilogram per minute based on your value for the 1.5 mile run. So again, our best estimate of your VO2 max is, our Y predicted in this case is 50 mils per kg per minute based on your score for the 1.5 mile run. 68% of the actual scores on VO2 max for someone with your score on the 1.5 mile run will be between, now I take my prediction, which was 50. I subtract 1 standard error of the estimate. Let's, for purposes of this example, say that the standard error of the estimate was 5 mils per kg. We predicted 50, okay? So now we can say that 68% of the actual scores on the VO2 max for someone with your score on the 1.5 mile run will be between 45 mils per kg and 55 mils per kg. Essentially, I've taken the prediction score, I've subtracted 5 mils per kg, and I've taken the prediction score and I've added 5 mils per kg. So 68% of the time, I've told you your VO2 max is 50 mils per kg, but that's only an estimate. It turns out that 68 or 2/3 of the time, it's actually going to be between 45 and 55 mils per kg, because the standard error of the estimate that we've calculated, let's assume that that's 5 mils per kg. Similarly, 95% of the actual scores or values on VO2 max are going to be between 40 mils per kg and 60 mils per kg. How did I get those values? I took my standard error of the estimate, which was 5 mils per kg. I multiplied it by 2, and I subtracted it from the predicted score, which was 50. That gives me 40 mils per kg. I added 2 times 5, or 10 mils per kg, to my predicted score of 50, and I got 60 here as the way to fill in this second blank. So, there's lots of simplified ways of looking at this. If you've kind of lost me on this video, please go back, reread those 3 pages in your book, page 64, 65, 66. And you can see here that when we predict somebody's pull-ups from their body weight, we get an interpretation that reads like this, all right, when the standard error of the estimate is 2.28 pull-ups. So you're actually going to have to pull out your book. You're going to have to see that the standard error of the estimate can be easily calculated. Again, this is not a hard number to calculate. We estimate it by plugging in these numbers. Once we have the SEE, we then can come down here and make a simple interpretation. You have a predicted score that's this. We have a standard error of the estimate that's this. We take 68% of the people who weigh this. We think they're going to fall in this range. We take 68% of the people. This should be a 95. I think there's a typo here. And 68, please check pages 64 through 66 of your book. I'm sorry for that little error here. Again, I put this in red. I've highlighted it. I'm hoping at this point that you're starting to see the connection between the fact that the standard error of the estimate you interpret just like a standard deviation, because that's what it is. It's the standard deviation of the errors of prediction. There are last couple of points here. When we make up prediction equations, we do a process called cross-validation to make sure that it's going to work in other populations before we apply that prediction to the general public. And the last topic here is multiple prediction. I've already gone through this pretty well on the slide presentation. Instead of having a single predictor, we have multiple predictors. The multiple regression equation takes this form, and we usually can come up with a higher R value. That's a big R in this case. A higher coefficient of determination when we have multiple predictors, and therefore less error when we use multiple predictors to come up with a prediction or an outcome as opposed to a single one. Sometimes you're going to see multiple regression equations written like this. There's an exponent involved because it's a polynomial regression. It's just not a linear equation. There's a different formula. And most of the true equations for predicting body fatness from skin fold, they look something like this. This is actually a regression equation. We're predicting body density in this case. We plug in all of these numbers. Notice that in this case, we take the sum of the 3 skin folds, we square it, we multiply it by this term, then we put it back into this equation, and we can actually predict body density. And then you take a person's body density, and you take 495 divided by that body density, you subtract 450, and now you're going to come up with their percent fat. This is a multiple regression prediction equation, only it's not linear. It's going to be curvilinear. It's going to be exponential. It's what we call polynomial because it involves exponents. I just want you to be familiar with that in case you see that out there. The last bit of information is, let's go back to working with real people. You're going to be predicting falls. You're going to be predicting VO2 max. You're going to be predicting body fatness. So what you're going to do when you meet with a person is you're going to tell them what their predicted score is. And you're going to tell them how they did relative to other people. You're going to give them their percentile rank. And then if you're really good, or if they ask questions of you about how accurate the prediction is, you're going to interpret for them essentially what is the standard error of the estimate, what is the error of prediction, so that they know what that will mean. Please take some time to go through these sample problems. When I'm back, I'll review them with you, but I think this should give you a good start in getting through everything you'll need for the homework assignment. Thank you.